Hi there guys, so in this video I'm going to go through exercise 12F question 1. Now each of these parts will probably take you a page or 2 pages of working out. They are huge questions. So I'm not going to do all of that in this video. I will do it fully for the second part. In the first part I'll concentrate on the phase portrait. And in the third part, I'll concentrate on the shape of the phase portrait. So the particular gradients, finding those particular gradients, the dy dt, dx dt at particular points, and in fact dy dx as well at particular points. And then for the fourth part, I'll just do the phase portrait. Okay, now before I go into doing those ones, it should be noted that I didn't notice that there was a mistake in the book in this penultimate paragraph on page 551. Now, it's possible that in future versions of the book they will change the wording of this, but I think it is wrong. In fact, I'm completely sure that it's wrong. So I've just set this one up here, and it says this. It says when both eigenvalues are negative. So when they're both negative. Now, this is the example from this exercise 12F, and this is question 2, and it's diagram D, which matches up with the solution set from your capital B. So it's these two which match up quite nicely. They're actually next to each other. So in this case, we can see that we have two eigenvalues which are negative. We have -1 here, and we have -3. And it says in the book, so I'm looking in particular at this statement here, which was on page 551. It's the penultimate paragraph, as I say. So it says when both eigenvectors are negative, all trajectories move towards the origin as t increases. Now that's fairly obvious. We can see that over time, this is going to get smaller. So if we did e to the -100, if t is 100, we can see that that's going to get extremely small compared to e to the -1, for example. So over time, this is going to get smaller, and likewise, this is also going to get smaller as well. E to the -3t is a decreasing function, so it's going to get smaller. So it's going to bring us into 0. So both of these are going to bring us into 0 here. So this is a stable equilibrium point. Okay, we're happy about that one anyway, and that's definitely we're going in this way and we're going in this way. No problem with that. But then it goes on to say, and towards the direction of the eigenvector associated with the more negative eigenvalue. Well, the more negative eigenvalue here is -3. Now, -3 is associated with this direction here. That's this direction here. So over time, we should end up going in this direction here. But you can see that if I take a point, let's say this point here, that over time we end up going in this direction. We get sucked in to this direction here. And likewise, if I took a point here, say for example, we're going to get sucked in over time into this direction. That's how I interpret it. Now, if you go backwards in time, sure, you end up going in the direction of this vector here. But as we go forwards in time, we get sucked in to the other vector. So we get sucked into this vector here. Now, actually, this is a pretty good thing because it makes this entire paragraph much easier. Because we can simply say that in all cases, over time, we get sucked into the direction which is associated with the highest eigenvalue. And that would be the same in all cases. So let's look at the first one here. So in the first statement, it says, as t increases and towards the direction of the eigenvector associated with the larger eigenvalue. That's when they're both positive. So for example, if we had 3 and 4 as our eigenvalues, the eigenvector associated with this is the direction that we would tend to over time. Now, in this case, as we're seeing here, if we got the two eigenvalues, -1 and -3, we can see that we're ultimately going in the direction associated with the eigenvalue -1, the larger of the two. And again, if we look at the last part here, again it says the eigenvectors move towards the direction of the vector associated with the positive eigenvalue. So again, if we have one which is positive and one which is negative, I don't know, let's say, for example, -2 and 1, then we would still be going in the direction of the larger one. So in all cases, we end up over time going towards the direction of the larger of the eigenvector associated with the larger eigenvalue. Okay, so I think that this is wrong in the book. However, what I'm going to do now should hopefully make everything clear if you go through each of these examples carefully. Okay, so let's have a little look at the first of these questions. And so first little question, let's take this thing here. So we're trying to find the solutions of the differential equations and draw the phase portrait. So this is our first question. Now, I'm going to take the answer from the back for this one, but I will work through it fully for the second one. So, by the way, the reason that I'm doing that is because in the original book, there's a mistake in the answers in the back for the second one, whereas there isn't for the first one. Okay, so the solution that you should get for your differential equations is x underlined, so which is obviously equal to x, y is our solution. So there's really a solution for x and a solution for y, of course. We're getting 2e to the 4t here, and then that's 1, 1, and then plus, this is just coming straight from the back, e to the minus 3t, and minus 2, 5. Okay, so we're going to try and draw the phase portrait for this one. So phase portrait, we can see that we're going to have two lines. We're going to have the 1, 1, which is going to be 1 across and 1 up. So that's going to be associated with this line here, y equals x. And I'm going to write down as well, which they don't in the back, I'm going to write down that lambda 1 is going to equal to 4. Okay, so that's equal to 4. And then minus 2, 5 is going to be 2 backwards and 5 upwards. So the point is going to be somewhere around here. So I'm just doing this roughly to scale here. It should go something like this. Now this is the graph y equals minus 5 over 2x. Okay, so again, you can get your gradient by simply doing, you've got that point there, which is minus 2 backwards and 5 upwards. So you can simply do your y value, your change in height, divided by your x value there to give you your gradient in this case. Okay, so there we go. We've got that, and I'm also going to write down here that we've got lambda 2 is equal to minus 3 here as well. Now, according to the rules, we move towards, ultimately, the eigenvector, which is associated with the larger of the two eigenvalues. So we're going to move towards this over time. Now, because this one is positive, because this eigenvalue here is positive, then we're going to end up going away from the origin. Because this eigenvector is negative here, we're going to end up going towards the origin for that one. Again, that's quite simply understood by saying that this over time tends to 0, and this over time becomes larger over time. Okay, so that's pretty straightforward at the moment. We can see that we've got a saddle point in this case because we don't have a stable equilibrium. We can see that we are we're going away on one and towards on the other line. Okay, so my top tip with drawing these phase portraits is to say, take a point which is somewhere close to the line which we're moving away from, and then move in the direction over time towards the other one. Okay, and so likewise, take something which is close to the one which we're moving away from, and then towards the other one. So it's going to look something like this. Now, in the book, some of these get much, much closer over time to this axis, and some of them, if you go backwards in time, are much closer to this axis. I think that's really overthinking things, though. You should be able to draw this diagram, and we're not going to worry about these things getting extremely close quickly. Yeah, so this one is fine. So there's our phase portrait in this case. My addition here would be two things compared to the book. I would say put in your lambda 1 and your lambda 2 associated with those lines as well. And then also take points which are close to the line that you're moving away from, as far away as possible, really, and then draw your smooth curves in towards the other one. Okay, so this is a pretty easy one to draw. Of course, this one is a saddle point, and obviously it's not a stable equilibrium. We're not tending towards 0, 0, and neither is it a source because we're not emanating from 0, 0 there as well. Okay, so for the second one, I'm going to do the full working out. So if you're happy with the full working out, you can skip forwards, but I would really suggest having a look at how I do each of the phase portraits. I think that's the really difficult thing about this exercise. Okay, so next one. So let's take this then. So next one is this. Okay, now in terms of doing this, let's set it up fully here. So this took me about a page of working out. I might struggle to fit it on here. First of all, we should be able to set up our matrix quite quickly here. We've got our 1, 2, 0, 3, which are just coming from the coefficients of x and y in each of these cases. Now, I'm going to show you this properly because what we're really doing is saying we're applying this to xy to give us x dot, which of course is actually dx dt, and y dot there as well. Now, that's also equal to some lambda times by xy. So I'm going to just go back and show kind of why what we're doing is true again. So that's also equal to this. So in other words, we're replacing this with some eigen value in this case. We can sometimes replace matrices with eigenvalues. And assuming that we're looking for eigenvalues, it must be true that we can do that in this case as well. Okay, so if we kind of ignore this thing and take this to the other side, then we can combine this and this when we take this to the other side to equal the 0 vector. So we can do that by then saying 1, take away lambda, applied to x, of course, and then the 2 is not applied to y in that first case. And then we've got 0 and then 3, take away lambda, and then that's applied to xy, and that gives us 0, 0. So essentially what we've done is we've taken this to the other side, and then we've done some matrix algebra there. We've taken off lambda, and essentially we've come up with this extra matrix here, because obviously this as well is equal to lambda identity matrix xy, and that's also equal to lambda 0, 0, lambda xy. And then of course when we take it across to the other side, take this to the other side, we end up taking away lambda in this position and this position here. So that's why we end up with this thing here. Okay, obviously we've done that before, but just recapping on why we're doing what we're doing again. Okay, so at this point, we need to, in order to solve this for our eigenvalues, we need to set the determinant of this matrix. So the determinant of M, if we can call this matrix here now, M, is going to be equal to 0, and that will give us 1 minus lambda times by 3 minus lambda, and then minus these two times together, which is obviously 2 times 0, is going to give us 0. Okay, now since this becomes 0, we can quite easily see that to get a 0 here, we'll need to put in lambda is 1 here and lambda is 3 here. So our two values here is lambda is equal to 1 and 3. Okay, so 1 and 3. So now when we've got those eigenvalues, we've got the 1 and the 3, we then need to go back to this, so put them back in there, and then come up with our eigenvectors. So if we go lambda 1 is 1, then when we put this back in here, we can see that we're getting 1 take away 1 is 0, and then 2, and then 0, and then 2 again there. And we take away the 1 in this position here. So as we expect, it's giving us two equations here, which are the same. And in fact, in each of those cases, you're simply getting out 2y equals to 0. So this gives you 2y equals to 0, or equally, y is equal to 0, and that's the eigenvector. So y is equal to 0, remember, is the x-axis. So the x-axis would be 1 across and none up. Amounts of that would take us across the x-axis. So amounts of this vector would take us up and down the x-axis here. So this would be this would be like the most obvious eigenvector to use in this case, but obviously you can use 2. You could use -1 there as well, but you're not going to see that in the answers. But it would be okay. The thing, if you had a 2 here, it would just change your a value, which we're about to find out. It would change your a value by halving that. So it would affect that constant which you have in front of your e to the eigenvalue times by your eigenvector. It would affect the value of the constant if you change this value here. Okay, so we want to do exactly the same thing for lambda 2 as well. So for lambda 2, we have the answer of 3, and when we substitute that in, we can see that we're getting -2 there and 2, and we're getting out for the next one 0 and 0 applied to xy, giving us 0, 0. And we can see that we can only really get out the equation of the line from the top part there, which is giving us -2x plus 2y is equal to 0, which then gives us y is equal to x. Now, y is equal to x, of course, the most obvious eigenvalue to use for this one would be 1, 1, the most obvious eigenvector, sorry. Okay, so to come up with our full set of solutions here, we then need to say we've got our x underline, which of course is xy. Okay, so there's xy there. So this x underline is going to be equal to a, and then times by e to the t, so 1t, and then 1, 0, and then plus b e to the 3t, and then 1, 1. So there's our solution, but now we need to use this initial information in order to work out what a and b are, and that's pretty straightforward. So the mistake in the book, by the way, in the original printed copy of the book, was that they gave this as something like 2 minus 5 or something. They made a mistake here. So this was the mistake in the book. This is why I'm going through this one. Okay, so finally then, we're going to need to make some substitutions in here, and we'll need to put in t as 0. Now when t is 0, this is going to become 1, and this is going to become 1. So both of those are going to be 1 when t is equal to 0. And then you're going to get out x is 3 and y is 1. So that's going to give you 3, 1 is equal to this thing. Now that's going to give us a set of simultaneous equations. So that's going to give us 3 equals a. So I'm just following the top line here. Plus, struggling to write a little bit on my new laptop. So we've got a plus b, and that's coming from the top line. So that's just coming from 3, a times 1 times 1, and b times 1 times 1 there. And the bottom line would be 1 equals a times 1 times 0, and b times 1 times 1. Meaning, of course, that we're going to get out 1 is equal to b. Now, if we've got 1 is equal to b, then of course a is equal to 2 from this simultaneous equation here, the simultaneous equations which we have. So now we've solved these, and we can restate the original set of solutions, your x underline here, your vector for x, which is of course xy. Okay, so that is done. Right, now let's do the phase portrait for this one. So let's just restate this again. So in this case, we've got x is equal to 2e to the t, 1, 0, plus 3, not 3, b was 1, e to the 3t, and 1, 1. Okay, so in order to draw this phase portrait, we need the two vectors drawn to start off with. So these two directions. So we've got this one, we've got 1, 1, and we've got 1, 0. So that's this one here. So this is going to be associated with lambda 1 equals to 1. And this is going to be associated with lambda 2 is equal to 3. And of course, you can come up with your equations there. Y equals x and y equals 0. Okay, let's write that in. Y equals 0 and y equals x. Now, we need to know which one we're tending towards over time. So we tend towards the eigenvector associated with the larger of the two eigenvalues. So we tend in this direction here. So we're going to tend to this direction over time. Now, they're both positive. So we both of them are going to go away from the origin in this case. So this is a source. And just make sure I got this one right. So we're going to go towards this way over time. Now, what I would suggest is that you pick a point, again, on the vector which you're going away from, rather than the way which the vector which you're going towards. And I would pick that at the start of its journey. So in this case, I'm not going to pick a point over here because we're moving away from the axis. So I'll pick a point somewhere around here. And if you take that point, you'll see that you're going to need to end up going in this direction here. So something like this. So again, you can put on more than one line. So we're going to go something like that. And, they're going to end up going like this. These ones are going to be slightly closer to this trajectory here. Now, likewise, you can do the same on the other side. So we're going to end up going like this. Okay, so we've got those ones in. Those are the easier part here. Now, the more difficult part is to do this sort of area here. Now, again, I would take a point which is close to here, and we've got to go to start off with like in this direction, but we've got to end up going in this direction. So what's going to happen is it's going to pull it around like this. So it'll go something like this. And likewise, you can do the same here. We can go like that, something like that. So there you go. That's the full diagram here. Now, if you're unsure about this, what you can do is check dy dx at a particular point. So, for example, if you wanted to check what's happening, say, let's go somewhere in the middle of the two of them. So let's say somewhere here. Okay, so let's check this point to see what's happening. And this point here would be, for example, let's make it easier. Okay, let's just take this point here. Okay, so this is the coordinate point. I don't know, let's say it's 0 across and 4 up. Okay, I'm just guessing there. I'm just guessing to my scale. So let's take that coordinate point and let's put it back in here. So if we do that, we can now see that x dot, or dx dt, is going to be equal to 2y there because the x is going to disappear. So 2y is going to give us 8. And y dot, in this case, would give us, so which is 3y, so that would give us 12. Now that says that over time, you can come up with a direction vector for this one if you want. We're going at the sort of speed per 1t of 8, 12. That means to say that we are going 8 across and 12 up at this point. So you can see my diagram there is actually pretty good. We're going roughly in this direction at that point. Okay, so we're tilting round towards y is equal to x, but we haven't quite got there just yet. And of course, you can choose any point you want to check that. And so this, importantly, gives us like a direction vector at that particular point. Now you could change that into a gradient as well, and you could actually do that by saying, well, dy dx is equal to dy dt, chain rule here, times dt dx. Now, dy dt is equal to 12. dt dx is the same as 1 over dx dt, so that's times by 1 over 8. And there we go, we can see we've got a gradient there of 1.5. So again, we could either use this or we could use the 1.5 to come up with our direction vector at that particular point. So it would indicate whether or not we've got our arrows going in the correct direction or not. Now, if you wanted to check a point over here, you'd probably see that we're going in this direction, although I don't know quite how fast it turns. Okay, so let's do part 3. In part 3, again, I'm going to check a couple of points here, and yeah, I'm not going to do the full working out for part 3. So part 3. So let's have a look. Yes, there. Part 3 on this one. Here we go. So for part 3, we've got dx dt, dy dt. We can come up with our matrix if we want to. I'm not going to do that just at the moment. I'm taking this answer from the back of the book. So we've got the equation in this case, which is x underline. It's important to underline this, by the way, because x is a vector there. So then we've got 3, 1 second, pen's just turned off. So we've got 3e to the minus 3t. And then that's times by 2 minus 1 minus 4 lots of e to the minus 4t. E to the minus 4t, and then we've got 1 minus 1 there. Okay, so this is the example which contradicts the statement in the book. So the statement in the book, again, let's go back to this, is what I started off with in this video. It says in this penultimate paragraph here, it says that the trajectories move towards the origin as t increases when both of the eigenvalues are negative, and towards the direction of the eigenvector associated with the more negative eigenvalue. This is wrong. It ends up going in the direction of the larger of the two eigenvalues. In other words, the less negative one. Okay, so the less negative one in this case would be this one here. Basically, we're choosing minus 3 because minus 3 is bigger than minus 4. Okay, so we're going to need to go in this direction over time. Right, so let's draw this thing. So here we go. We've got this vector here, which is going to be y is equal to minus x, this graph here. So we've got y equals minus x, and that's associated with lambda 2, which is minus 4. And interestingly here, we've got a minus 4 there as well. Okay, and then for this one, we've got our 3e to the minus 3t here. So this is going to be going in the direction, so 1 backwards, 2 forwards and 1 down, sorry. So 2 forwards and 1 down, or in other words, using the gradient of minus a half. So it's going to be going like this somewhat. Okay, so that's going to be y equals minus a half x. That's going to be associated with the eigenvalue of minus 3. Okay, so over time, we're going to be heading towards this line here. Let's draw that a bit better. So this line here. Both of them are going inwards because this gets smaller over time and this gets smaller over time. So both of these go inwards. So we can put those arrows on. That's the easy part. Okay, and then between these two, it's going to be pretty easy as well. Again, choose a point which is on the eigenvector which we're moving away from at the start of its journey. So we're going to end up going, let's get this one right. So we're going to end up going like this over time. So it's going to go in. Obviously, anything which is close to this is just going to go sort of straight down. Maybe exaggerated that one a bit too much. And again, from this, over time, we're going to go towards this one here. You can put more arrows in. I'm just struggling here writing on my screen. And then for outside, it's kind of more difficult to show. If you took, so we can see that we're going to end up going in this direction, but if we start from here, how do we end up going towards this direction here? And that's the tricky bit to draw. So it's going to kind of go like this, go inwards. It's got to go sort of round, sort of curve round in this case. So we're going to kind of go like this and like this over time and like this. Okay, so, and this is going to kind of look pretty much like it's going straight at that point, but it will kind of turn in right at the end. Same on the other side. So again, if you'll be going pretty much straight there, but then here we'll be sort of going inwards and inwards and inwards like this as well. If you took a point over here, you can see that it would be pretty much going like this. But we've somehow got to get so that we're ultimately going round in this direction here. Okay, so there's our final diagram. Should look something like this. Yeah. Okay. Now, what I'm going to do is check a couple of points here again. I'm just going to check a couple of points to see if I've got this one right. In particular, I'm concerned about this area here. So, I mean, I could check this point here. I'm going to actually check something which seems to me directly in the middle of these two lines. So I'm going to check a point up here, which is the coordinate point 2, 4. So that's the first one I'm going to check. And the second one I'm going to check is a point here. I'm going to check the coordinate point 3, 0. Now, the way in which I can do that is simply by looking at these two. So I can see I've got x dot for the first of those 2 points there is going to be minus 2 times by 2, so it's going to be minus 4, and then plus 2y, so plus 2 lots of 4 is going to give us 8, so that gives us 4, and y dot is going to be equal to minus 2 and then minus 20 there, so we're going to end up getting minus 22 there. Okay, so that's minus 22. So that's going to essentially give us the vector, the movement vector over time of 4 per 1 second or per t at this point, 4 and minus 22 there. Now you could put that into a gradient as well if you wish to. Again, as I said before, you can do dy dx is equal to dy dt, which is minus 22, times by 1 over dx dt. That's the chain rule. So that would be times by 1 over 4. And that would give us minus 5.5. Or we could indeed find a gradient from this as well. We'll just do minus 22 divided by 4. Okay, so minus 5.5 would indicate that we are going, let's do this, we're going roughly in this direction here. So for every one we go across, we go minus 5.5 down, or 5.5 down rather. So it seems to me that I've got this diagram roughly right here. We're going roughly in this direction at that coordinate point. Okay, so we could say there m equals minus 5.5. And by the way, we also know we're definitely going from the top left to the bottom right there because we know we're increasing in x, so in this direction, and we know we're going down in y, so in this direction here. So the gradient alone doesn't tell us whether we're going in this direction or this direction. Yeah, so we actually need this vector really to tell us whether we're going, which way that gradient is actually traveling in. Okay, well, you could probably do that simply by looking at dx dt, because dx dt would say this direction, which would mean we must be going this way here. Okay, so let's do it again for the next one as well. So let's do it for this 3, 0 here. So this point, again, there we're getting x dot, 3, 0 is minus 6 there, and y dot would be equal to minus 3. And you can see that's giving us the direction vector of minus 6, minus 3. Or if you like, that's the gradient of a half. So gradient of a half, so we're going like this, gradient of a half, but we're going backwards and we're going down. So we must be going in this direction here. Okay, so you can see we've got this diagram pretty much right. Okay, so last one. By the way, this is a stable equilibrium point. Previous one was a source. And the next one, I believe, is going to be another saddle point. So let's do the next one fairly quickly. So next one, let's say we've got x underline, and we've got 3 e to the minus 5t. And we've got minus 1, 3, and then plus 2 lots of e to the 2t. And then 2, 1 there. Okay, so again, we're going to be traveling in the direction of the larger of the two eigenvalues, this one here, which is the direction vector associated with that, which is this eigenvector. So we're going to be traveling in that direction. So let's come up with this. 2, 1 is going to be 2 across and 1 up, will be this line here. So that's y equals a half x, and that's lambda 1 is equal to 2. And then we've got minus 1, 3, so we can draw that one quite quickly as well. So 1 backwards and 3 upwards, something like this. So we're going through that point, it will go through the center. So that's going to give us the line, what should be a straight line there, is minus 3x, and lambda, probably should call that one lambda 1. Lambda 1 is equal to minus 5t, so that's lambda 2 there. Okay, so to draw this one, we're going to go in this direction, of course. So that's this direction here over time. We can definitely see that this one is positive, so it's going to be like this. And this eigenvalue is negative, so we're going to be going towards the origin there. So again, saddle point. And this one's dead simple to draw, in fact, because if we took points which are close here to the line which we're moving away from, and you should see that we're going something like this, and something like this, and like this, and like this. And saddle points are pretty easy to draw. Okay, so that is done. Thanks for listening in. In the previous exercise, I went through, or previous video, I went through question 2 basically towards the end. Yeah, and there was a mistake in part B. So let's look at that briefly as well. So in part B here, we realized we need to copy the other thing. So let's make this a little smaller. If you already saw the previous video, then fine. But part B matched up with, so this was a saddle point here. So one is positive, one is negative. Part B, I think, we also have this line here, which is going to be the eigenvector 1, 0. So which one's got 1, 0? That's this one here. So A associates with this thing. Okay, so this matches up with this one up here. Now, in that case as well, we're talking about we're moving towards the eigenvalue, moving towards the eigenvector associated with the positive eigenvalue, because we have one which is positive, one which is negative. So we're moving towards this over time. So we should be moving towards this over time. So they've made a mistake there, because we should be going in, should be sucked in towards this way. Okay, so we should be going the other way around. So the arrows are the wrong way around in that diagram. Okay, guys, well, good luck with the exercise. Obviously, get as much practice as you possibly can. There's a ton of practice there. It's going to take you quite a while to do. Good luck with that, and thank you for listening in.